Quantum entanglement opens up the exciting possibility of communication between our universe and others. At its core, entanglement describes the phenomenon of two or more particles becoming interconnected in such a way that the state of one instantly affects the state of the other, regardless of the distance separating them. This unusual behavior challenges the classical understanding of entanglement and locality, suggesting that information can be transmitted over vast distances in ways that are inconsistent with our traditional notions of space and time. In the context of multiple universes, often referred to in theories such as the multiverse, entanglement can serve as a bridge between these realities. If entangled particles come from different universes, then a change in one can have an immediate effect on the other, regardless of physical separation. This connection suggests that the boundary between universes may be more permeable than previously thought, allowing for a shared reality beyond the isolated conditions we perceive. Moreover, some physicists hypothesize that entangled states may exist outside our universe, implying that quantum information can be transferred between multiple universes. For example, each entangled state may represent a connection not only to our universe, but also to others existing nearby within the larger multiverse. Consequences is an exciting frontier in modern physics. While researchers continue to unravel the complexities of quantum mechanics, the implications for our understanding of the structure of the universe and the possibility of existence beyond it force us to reconsider the nature of reality itself, suggesting a universe that is richly interconnected. Quantum decoherence is a fundamental process that plays a crucial role in the transition from the strange behavior of quantum mechanics to the classical world we observe every day. At the quantum level, particles can exist in superposition, where they occupy multiple states simultaneously. However, when a quantum system interacts with its environment, this fragile state begins to break down. As a result of this interaction, the superposition of states disappears, leading to a single valued result. This phenomenon helps explain why we do not see the unusual behavior predicted by quantum mechanics in macroscopically large objects. The connection between quantum inhomogeneity and the theory of parallel objects is interesting. Many interpretations of quantum mechanics assume that all outcomes arise from one large event, leading to multiple concurrent or universal phenomena. In this system, transactions resulting from neutrality are strictly isolated from such situations. If the quantum system is not balanced, the different states will be separated and become non-reciprocal branches of reality. Thus, what may appear to be a single universe is actually a vast tapestry of branching scenarios, each branch representing a different outcome of each quantum event. Decoherence provides a critical mechanism for understanding how these parallel realities can coexist without interfering with each other. Once a quantum system becomes entangled with its environment and experiences decoherence, the outcomes become virtually independent. This separation allows each reality to develop its own unique history, ensuring that the many possible worlds remain distinct from each other, even if they emerged from the same quantum state. This results in a multiverse in which the outcomes of quantum events lead to the birth of different realities. Furthermore, understanding quantum decoherence has profound implications for fields such as quantum computing and information theory. It highlights the challenges of maintaining quantum coherence in systems designed to exploit quantum properties for technological advancement. As researchers continue to study decoherence and its role in the quantum realm, the implications for our understanding of parallel realities and the structure of the universe grow deeper, bringing us closer to comprehending the complex nature of existence itself. The multiple interacting worlds interpretation of quantum mechanics presents a fascinating view of parallel universes, extending traditional interpretations in the field of quantum mechanics. This interpretation differs from others, such as the Copenhagen interpretation, in that it eliminates the need for the wave function to collapse at each dimension. Instead, it assumes that all possible outcomes of quantum events are realized in separate but interacting branches of existence. According to this interpretation, when a quantum event occurs, such as the measurement of the position of a particle, the universe does not decohere into a single state, but decomposes into many coexisting realities. Each of these facts corresponds to a different quantized measurement result. If, for example, a particle has a 50% probability of reaching one state or another, the two outcomes will occur in different branches of the universe according to the definition of a multiverse. However, these branches are not entirely separate. They retain the ability to interact on a large scale. What is really interesting about the multiple interacting worlds interpretation is the idea that these parallel worlds can influence each other. Interactions can lead to interference patterns similar to those observed in quantum systems. For example, outcomes in one branch of reality can influence the behavior of another. This interaction involves a complex web of interconnected universes, creating a framework in which our choices and actions resonate with the wider tapestry of existence. This interpretation of quantum mechanics adds another layer of richness to our understanding of reality because it suggests that instead of experiencing one linear line of events, we are part of a much larger, interconnected multiverse. Every decision or accident we make unfolds pathways that lead to multiple, simultaneously existing realities. This offers a fascinating perspective on our existence, emphasizing that quantum mechanics can govern not only the microscopic world, but so too does the very fabric of reality itself, weaving our experiences with countless parallel stories. Experimental evidence for quantum effects at cosmic scales emphasizes the remarkable interconnection between the microscopic realm of quantum mechanics and the vast universe. One of the most compelling examples is the phenomenon of the cosmic microwave background radiation, which is thought to be residual light from the Big Bang. Tiny temperature fluctuations in this radiation, measured by satellites such as the Wilkinson Microwave Anisotropy Probe, are evidence of quantum fluctuations in the very early universe. These fluctuations set the initial conditions that led to the large-scale structures we observe today, such as galaxies and galaxy clusters. Another important piece of evidence is the study of large-scale entanglement and quantum coherence in a cosmological context. Studies of the behavior of light from distant sources have shown that quantum effects can persist over vast distances, challenging our understanding of separability in classical physics. Experiments with pairs of entangled photons point to the influence of quantum mechanics at cosmic scales, as these photons retain their entangled state despite being separated by significant distances. In astrophysics, the study of supernovae and neutron stars has provided additional insights into quantum effects on cosmic scales. These events create extreme conditions in which quantum behavior becomes key. For example, the behavior of dense matter in neutron stars is governed by quantum mechanics because they consist mainly of neutrons organized into quantum states that cannot be described by classical means. Observations of pulses, which are neutron stars emitting beams of radiation, also suggest that quantum processes are at work in their rotation and electromagnetic emission. In addition, the quest to detect gravitational waves has led to experiments that simultaneously explore quantum mechanics and general relativity. The Laser Interferometer Gravitational Wave Observatory uses highly sensitive quantum technologies to measure gravitational waves arising from cosmic events, such as black hole collisions. The precise nature of these dimensions, which depend on quantum effects, bridges the gap between the quantum realm and the cosmic landscape, This reinforces the idea that quantum mechanics is not limited to the tiny scale of atoms and particles, but permeates the universe itself. This body of evidence inspires further research into the fundamental connections between quantum physics and cosmology, showing that the universe is more interconnected than we previously believed. Using quantum entanglement to communicate or interact with other universes is an intriguing concept that opens up possibilities far beyond our current technological capabilities. Entanglement allows pairs or groups of particles to bind together in such a way that the state of one particle directly affects the state of another, regardless of the distance separating them. This unique property raises the question of how entangled particles can facilitate communication between different universes, especially within the concept of the multiverse. One theoretical approach to using quantum entanglement for inter-universe communication involves creating entangled pairs of particles in different branches of the multiverse. Assuming that these branches can interact through quantum processes, changes made to one entangled particle can instantly affect its partner in another universe. This suggests a mechanism by which information can be transferred or exchanged between realities, although the practical aspects of such communication remain in the realm of speculation. Another avenue for exploration involves the concept of quantum teleportation. This process uses entanglement to transfer the quantum state of one particle to another without physically moving the particle itself. If we could create a method of teleporting quantum states between universes, this would allow the transfer of information, or even the particles themselves. However, serious problems remain here, as this would require a sophisticated understanding of the connections between quantum states of particles in different universes and the means to maintain delicate entangled states over such vast distances. In addition, entangled particles can provide insight into the nature of parallel realities by studying how their states can differ or correlate. By measuring the results of particle entanglement in our universe, we can obtain information about the corresponding states in other universes. This experimental research could pave the way to understanding the physical laws governing these realities and how they relate to our own. While the concept of using quantum entanglement to interact or communicate between universes is deeply theoretical and fraught with difficulties, it provides an exciting window into the potential possibilities that future technologies may one day achieve. As our understanding of quantum mechanics advances, the quest to comprehend the boundaries between universes may bring us closer to realizing the extraordinary implications of an interconnected multiverse. Cosmic voids are vast empty spaces in the universe that contain very few galaxies and matter compared to denser regions. These voids can span tens to hundreds of millions of light-years and make up a significant part of the large-scale structure of the universe. Unlike the filaments and clusters where galaxies gather, cosmic voids appear as a great void, emphasizing the complex web-like distribution of matter in space. The study of cosmic voids has shown that they are not a simple absence of matter, but rather play a crucial role in the evolution and behavior of the universe. These regions can influence the motion of galaxies and affect the distribution of dark matter through gravitational effects. As galaxies move through space, they tend to cluster at the edges of these voids, creating boundaries that define their structure. By observing the properties and distribution of voids, astronomers gain insight into the overall dynamics of the universe and the processes that shape it. The connection between cosmic voids and regions outside our observable universe is a subject of great intrigue. Because cosmic voids represent some of the largest structures in the cosmos, they may indicate that similar empty regions exist beyond what we can currently observe. The universe continues to expand, and light from distant regions may not yet reach us, leaving the possibility of vast regions filled with voids or different structures beyond our observational horizon. Moreover, some cosmological models suggest that these voids may be related to the fundamental dynamics of the multiverse, where multiple universes exist in different configurations. If our universe is just one of many, the principles that govern the creation and arrangement of matter may operate differently in other realities, leading to different patterns of voids and structures. By studying the nature of cosmic voids within our universe, researchers can gain clues about the potential nature of regions beyond the observable boundaries, offering a tantalizing glimpse into the underlying fabric of reality. Supervoids are vast regions of space with densities well below average, often extending over hundreds of millions of light-years and containing far fewer galaxies than typical cosmic regions. These vast, sparsely populated regions contrast with denser cosmic structures such as galaxy clusters and superclusters. The existence of supervoids poses intriguing challenges to our understanding of the formation of cosmic structures, especially with respect to how matter is distributed throughout the universe. One important problem that supervoids pose is their impact on existing models of the evolution of the universe. Cosmological theories, especially those involving the distribution of galaxies and dark matter, are based on the premise that matter is relatively uniformly distributed throughout the universe, resulting in a sponge-like structure filled with filaments and voids. Supervoids, however, indicate that large regions of space can exist in relative emptiness, forcing scientists to reconsider how these vast voids formed without noticeable gravitational effects on surrounding structures. In addition, the presence of supervoids raises questions about the role of dark energy in cosmic evolution. Dark energy is thought to be responsible for the accelerated expansion of the universe, and supervoids may serve as natural laboratories for studying its effects. Observations of light from distant objects passing through supervoids have pointed to the possibility of distortions in the cosmic microwave background and gravitational lensing effects that can be used to study the effects of dark energy on cosmic scales. Understanding how dark energy interacts with these supervoids can enrich our knowledge of the dynamics governing the formation and expansion of cosmic structures. In addition, features of supervoids challenge our understanding of fundamental physics. For example, some researchers hypothesize that superwaves may be related to the existence of large-scale inhomogeneities in the universe, or even hint at the existence of complex cosmic phenomena, such as anomalies or exotic matter. This will provide new insights into the interplay between gravity, dark matter, and the fundamental forces shaping the universe. Studies of supervoids are ongoing, and they serve as a fascinating lens through which to refine our understanding of the formation of cosmic structures. Their study encourages scientists to further explore the nature of voids, growth processes in the universe, and the underlying principles governing the vast cosmic arena we inhabit. A cold spot in the cosmic microwave background radiation is a prominent region that appears significantly colder than surrounding regions. It was discovered thanks to measurements by satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, which analyzed the remnants of the Big Bang. This cold spot is unusual in that it covers a significant region of the sky, challenging standard cosmological models that predict a more uniform temperature distribution across the cosmic microwave background. One intriguing aspect of the cold spot is its potential connection to the concept of other universes, or the multiverse theory. Some researchers speculate that the cold spot could be the fingerprint of a collision between our universe and another universe. According to this idea, if two universes collide, the interaction could create localized effects in the cosmic microwave background, resulting in temperature anomalies similar to the cold spot. This hypothesis suggests that we are observing the remnants of a multiverse event, implying that our universe is not isolated but potentially part of a larger fabric of realities. In addition to the multiverse theory, Alternative explanations for the cold spot have also been proposed. Some scientists speculate that it could be the result of large-scale cosmic phenomena, such as structures forming during the evolution of the universe or arise from the gravitational influence of superwaves, vast, empty regions of space. Other theories point to possible systematic errors in measurements or the influence of our galaxy's background radiation, which may mask the true nature of this anomaly. While the cold spot remains a subject of intense study and debate, it serves as a stark reminder of the complexities inherent in cosmology. As researchers continue to study this intriguing phenomenon, its implications extend beyond our understanding of the cosmic microwave background, offering tantalizing possibilities for the existence of other universes and the interconnectedness of reality itself. Studying the nature of the cold spot could play an important role in uncovering deep truths about the structure of the universe and its place in the broader cosmic landscape. Cosmic voids, with their vast empty spaces and below-average density, have attracted the attention of scientists, suggesting that they may play a role in understanding deeper aspects of our universe, including the notion of other realities. These vast, sparsely populated regions may serve as windows or gateways to other worlds, especially when viewed in the context of theories about the multiverse. One way in which cosmic voids are connected to other realities is through their unique gravitational influence. Because of their lower density, voids can warp the fabric of space-time differently than denser regions filled with galaxies. This warp may create pathways through which we can observe or even interact with parallel universes, depending on the complex interplay of gravity and quantum mechanics. If there are other universes with special properties, the gravitational influence of cosmic voids could hypothetically allow for the influence of their fields, possibly leading to the observed effects in our universe. Moreover, the very nature of the voids is consistent with current theories of cosmic expansion and structure formation, which often predict the existence of other dimensions or universes. Some physicists suggest that the vast emptiness of voids may provide evidence for the existence of boundaries between our universe and others. In this scenario, voids may represent areas where the fabric of reality is less dense or has a different configuration, giving hints of other, perhaps more exotic realms that have a close connection to our own. In addition, the study of voids may shed light on the fundamental structure of space-time itself. If cosmic voids are accompanied by other dimensions or hidden spheres, they may open up insights into how matter organizes and evolves in the universe. Future discoveries in the study of voids may open the door to theories of interdimensional interaction, inspiring the exploration of ideas reminiscent of quantum entanglement that connect different realities. These scientific investigations are pushing the boundaries of our understanding, inviting us to consider whether the empty spaces of space are simply voids, or whether they are gateways to a wider multiverse waiting to be discovered. Exploring the cosmic voids holds the potential for significant discoveries about the universe and the possibility of alternate realities. By exploring these vast spaces, scientists hope to discover connections that could expand our understanding of existence itself, pushing us toward new theories and possibilities that will enrich our understanding of the cosmos and our place in it. Various observational methods are used to study cosmic voids and reveal their properties, which deepens our understanding of these amazing structures in the universe. One of the main methods is based on large-scale studies of galaxies and their distribution across the sky. Studies such as the Sloan Digital Sky Survey collect extensive data on galaxies' positions and redshifts, allowing astronomers to map large-scale structures. By analyzing the density of galaxies in different regions, researchers can identify voids and characterize their sizes, shapes, and environments. Another important technique is gravitational lensing, which studies how the presence of mass, such as galaxies or dark matter, can distort light from more distant objects. In regions of voids where gravitational influence is weaker, lensing effects can provide insight into the distribution of matter and dark energy. By studying how light is deflected from sources behind cosmic voids, scientists can infer the distribution of invisible mass and estimate the effect of voids on surrounding structures, which provides insight into the overall dynamics of the universe. In addition, the background cosmic microwave radiation provides a powerful tool for studying cosmic voids. Temperature fluctuations in the cosmic microwave background reveal the influence of large-scale structures, including voids, on the early universe. Scientists analyze how voids may have affected these temperature patterns, providing insight into their formation and evolution. This approach is particularly useful for understanding the relationship between voids and the cosmic web, as well as their role in the expansion history of the universe. In addition, simulations and computer models play an important role in the study of cosmic voids. By modeling the evolution of the universe, researchers can predict how voids form and change over time under different cosmological parameters. By comparing these simulations with observational data, astronomers can refine their understanding of the characteristics and dynamics of voids. These combined observational techniques not only expand our knowledge of cosmic voids, but also improve our overall understanding of the formation of cosmic structures and the fundamental processes that govern the universe. The nature of time in regions outside our observable universe is a deep and complex topic that challenges our current understanding of cosmology and fundamental physics. It is generally assumed that in our observable universe, time flows uniformly, shaped by the curvature and expansion dictated by the general theory of relativity. However, when we think about regions beyond our observations, various factors suggest that the concept of time may be significantly different. One intriguing possibility relates to the idea that time may not be uniform or absolute in distant regions. According to some theories, as we move away from our observed limit, changes in cosmic structure, including density and gravitational fields, can alter the passage of time. For example, regions with different gravitational intensities can exhibit time dilation effects, where time moves slower in stronger gravitational fields. In regions outside our observable universe, where we have no empirical evidence, it is likely that very different mechanisms may be at work, leading to different conceptions of time. In addition, concepts such as cosmic inflation and multiverse theories introduce the notion that the fabric of space-time may not be entirely continuous. If our universe has undergone rapid inflation, this could imply the existence of other, possibly unconnected regions of space-time, each with its own unique timeline. These fields may not be bound by the same temporal rules, which raises profound questions about how events in these regions can unfold independently of the timeline of our universe. Interestingly, quantum mechanics hints at the non-classical nature of time itself. In some interpretations, such as those involving quantum entanglement or superposition, the rigid structure of time may dissolve, leading to scenarios in which time behaves differently. If these principles extend to regions outside our observable universe, this may suggest a reality in which time sequences are more fluid or less predictable. Studying possible time variations in distant regions not only expands our understanding of cosmological principles, but also pushes the boundaries of theoretical physics. Researchers who pursue these questions may uncover surprising discoveries that will revise our understanding of time, challenge our assumptions about its universality, and present new dimensions of reality. Causal disconnection refers to the phenomenon where certain regions of space become isolated from each other, preventing any form of communication or interaction between them. This concept stems from the concept of relativity, where the speed of light serves as a fundamental constraint on how fast information and influence can propagate through the universe. When two regions become causally unrelated, events occurring in one region cannot affect or be observed in the other because it would take longer than the age of the universe to bridge the gap. Regarding the limits of the observable universe, causality plays a crucial role in shaping our understanding of cosmological limits. The observable universe is defined by a spherical region around us, extending the distance that light has traveled since the Big Bang occurred about 13.8 billion years ago. Beyond this boundary are regions of space that we can never observe or interact with because the light or signals emitted from these regions have not yet reached us. These regions are causally unrelated to our own observable universe. As the universe expands, some galaxies or structures may extend beyond our observable space at speeds faster than the speed of light due to the expansion of space itself. This means that if these objects were once part of the universe we see, they may become hidden from us as the cosmic fabric stretches. Consequently, the cosmos may contain vast swathes of reality that will forever remain unreachable and unobservable from our perspective. The idea of causal decoupling also leads to interesting conclusions about the nature of reality itself. This means that there may exist regions in the universe with completely different physical conditions, possibilities, or events that we can never know about or influence. This disconnection raises intriguing questions about the overall structure of the universe and the possible existence of other connected realities beyond our observational limits, further deepening the mysteries of the cosmos and our place in it. Closed time-like curves, or LVCs, are a fascinating concept derived from the equations of the general theory of relativity, which allows for paths in space-time that loop in on themselves. Theoretically, this allows an object or observer to return to an earlier point in time. While our own universe appears to operate within the normal flow of time, the existence of closed, time-like curves is suggestive of how they might manifest in other universes or regions of space. One theoretical framework in which time-like closed curves may exist involves the concept of wormholes. Wormholes are hypothetical passageways in space-time that can connect distant points in both space and time. If a wormhole were passable, it could allow travel to an earlier point in time while creating a closed time curve. Although there is no empirical evidence for the existence of such structures, the mathematics of general relativity theory supports their theoretical possibility by suggesting that regions of spacetime can be configured to allow CTCs. In addition to wormholes, some cosmological models, such as those with rotating black holes known as Kerr black holes, can also produce closed, time-like curves. The unique geometry of spacetime around rotating black holes could theoretically create regions where time loops occur, allowing us to return to previous moments in time. This suggests that in regions of high gravitational influence and strong curvature, such as near a black hole, the nature of time may behave differently, potentially allowing the formation of time loops. Exploring the existence of time-like closed curves also leads to intriguing implications regarding parallel universes or multiverse scenarios. If many universes with different physical laws or configurations coexist, it is conceivable that some of them may support the formation of CTCs, and others may not. This variety of cosmic structures can produce very different temporal landscapes, challenging our understanding of causality and the linear progression of time. The idea of closed time curves raises profound questions about time travel and the nature of reality, but it also prompts deeper investigation into the very fabric of spacetime itself. As scientists explore the frontiers of theoretical physics, finding evidence to support or refute these ideas could ultimately expand our understanding of the universe and its potential complexities, enriching our view of existence beyond ordinary temporal boundaries. The concept of child universes refers to hypothetical miniature universes that may form as separate, distinct regions within a larger cosmic structure. The idea suggests that these smaller universes may branch off from our own through certain cosmic processes, giving rise to entirely new regions of space-time with their own unique physical properties and laws. This idea has attracted the attention of cosmologists, especially in the context of theories of inflation, black holes, and the multiverse. One way that children's universes formed is through cosmic inflation, the rapid expansion of space that occurred shortly after the Big Bang. At this stage, fluctuations in energy density could lead to the creation of localized regions where inflation continues, effectively giving rise to baby universes that separate from the parent universe. These nascent universes may expand and evolve independently of each other, eventually acquiring their own distinctive features, but at the same time being a product of the physical laws of the original universe. Black holes also offer a tantalizing avenue for the formation of baby universes. Some theoretical models suggest that inside a black hole singularity, space-time may behave so differently that it sets the stage for the emergence of an entirely new universe. If a baby universe formed in this way, it could remain completely detached from our observable universe, leading to regions where the physics could be dramatically different. Such separation may explain why we see black holes as regions of no return. The matter drawn into them can be channeled into the newly formed universe. The concept of infant universes is also related to the multiverse theory, which suggests that our universe is just one of an infinite number of universes. In this framework, tiny universes could be numerous, potentially constantly forming as a natural consequence of cosmic evolution. Each of these universes could bear the imprint of the parent universe, but develop unique traits that would allow for different forms of existence, physical laws, and even changes in the constants of nature. While the idea of baby universes remains largely theoretical, speculation about their existence challenges our understanding of reality and invites further exploration of the cosmos. While scientists continue to explore the fundamental principles governing the universe, the mechanisms of the formation of baby universes may provide insight into the interconnectedness of existence and the possibilities that lie beyond the observable boundaries of our universe. The arrow of time is the observed direction in which time seems to flow, usually from past to future. This concept is inextricably linked to the second law of thermodynamics, which states that in an isolated system entropy tends to increase, leading to the development of disorder. In the context of multiple universes, the arrow of time raises intriguing questions about how time evolves and behaves in potentially disparate realities. In a multiverse scenario, each universe could have its own arrow of time, influenced by specific initial conditions, physical constants, and the distribution of matter and energy. This means that while our universe exhibits a straight arrow of time due to the increasing entropy associated with its expansion and interactions, other universes may experience very different time flows depending on their unique structure. In some universes, there are possible scenarios in which the arrow of time behaves differently than in our universe. It may flow in the opposite direction or exhibit complex behavior influenced by their own internal dynamics. The evolution of multiple universes can also be inextricably linked to cosmic events and phenomena. For example, universes that have experienced different types of cosmological inflation or collapse may give rise to different time arrows based on their thermal histories and entropy changes. As universes evolve, their individual arrows of time may determine how structures form, how galaxies and stars evolve, and how life, if it exists, evolves within that framework. In addition, the concept of the arrow of time in the context of quantum mechanics enters into this discussion. In some interpretations, such as the multiple worlds interpretation, branching realities can be influenced by quantum events and superpositions. Each branch performing a measurement may display its own arrow of time, which differs from other branches depending on the results of the transaction size. This emphasizes the potential connection between the direction of time in the macrocosm and microcosm of different worlds. Overall, the connection between the arrow of time and the creation and development of the multiverse provides a deeper understanding of the fundamental nature of reality. By exploring these concepts, researchers are tackling the most difficult questions of time itself by examining how we understand the world and the various phenomena that occur outside our world.